So let me start the presentation. Yes. Can you see my screen?
Yes, sir.
All right. Okay. What is going on? I don't know. It seems there is some problem in the pane. It's not working. Just a minute. Let me change a few things. Okay, maybe notability is not working. So I'll just come back. So let me sort things down and come back. Yeah, now I think it is fine. All right. So what we know till now, your differentiability is the following. We know that for a function if, say we can take open or closed, whatever. Uh, yeah, let's take open. The following are equivalent. One is limit x tends to a, uh, c f of x minus f of c by x minus c exists. Second thing is there is or there exists a linear transformation t from R to R such that limit x tends to c mod of fx minus fc minus t of x minus c by mod of x minus c equal to 0. All right, we have seen this. The whole calculation we have seen, and this actually we know this. So this t can be interpreted as a real number, and then you can um, see these two are equivalent. All right. Now, why do we care about differentiability, right? So can you tell me? Anybody? Why do we care about differentiability? What do you think?
So there may be many reasons.
Yeah.
May-
So,
Maybe we want tangents. We may want to find out rate of changes. So,
mhm.
so there can be many reasons.
To know if it can be approximated affinely.
Yeah, but yeah, that is true. You approximate this one, but then how? Why is it useful?
So also local properties of a function like maxima and minima, or whether the function is increasing or
Mhm.
decreasing in nature, we can find that through different if the first derivative exists.
Right. So that is the point. You can actually understand the function. So in physics, you will be able to understand what this how the particle moves. A particle moved, right? So one need to understand that path, and locally derivative gives lot of stuff. In R, when derivative non-zero, you'll get something. When derivative is zero, you'll get something else. So lot of informations are encoded in the derivation, in the derivative. Lot of information about the function is encoded in the derivative. That is the main point. So we'll see one thing here. So you recall a theorem from continuity. Recall a theorem from continuity. So theorem is this. Let f from AB to R be a continuous function, then f of AB, the image is again an interval. Right? Is this true?
Yes, sir.
Yeah, so do you know the proof of this one? This is one of very important theorem in continuity. So if you don't know the proof or you don't remember the proof, you go back and look at the proof. This is very interesting. It is actually in R, two things are connected. One is compactness and the other is connectedness. So continuous image of a compact set is again compact, and continuous image of a connected set is again connected. Those two are more generalization of this theorem. Here both are combined, and it's just take closed interval or open interval or whatever. You look at its image. So you take closed interval in this particularly here in R. So then you get actually a closed interval in R. So open interval can go to a closed interval, but a closed interval cannot go to an open interval because of compactness. All right? Is this clear? Well, this theorem is known, just but what is this point? It means that the maximum and minima is attained, right? This theorem says that for a continuous function on a closed interval AB, the maximum and the minimum is attained or are attained, yes. That is, there exist CD in AB such that f of C will be alpha, which is infimum over AB of F, and f of D will be beta, which is supremum over AB of F. I mean Fx. All right. So this is by continuity. You know already, but we don't know which points are these C and T. All right. So one question is, what are those points where the max or mean is attained? Right? So the maximum or minimum, this has nothing to do with derivative at this point. The continuous functions on a closed bounded interval, you get maximum and minimum. And you know the existence of the points. The points may not be unique. So the points, so one thing is very clear, that such points may not be unique. So for example, fx is equal to sine x, right? So at x equal to pi by 2, right? 2 pi plus pi by 2, if x is 1, right? Which is the maximum. But there are a lot of points. Similarly for minimum. All right. So max mean here at this point, for existence of those points, you don't have nothing to do, there is nothing to do with derivative. But derivative is important to find the max mean because of the following reason. So it is important if you want to find precisely the maximum or minimum. Of course, not globally, locally. That I'll come. But in this case, if we take such things, so let me write it as theorem. So if instead of closed interval, let's take an open interval. Let f be a map from in open interval AB to R, be a differentiable function, and C belongs to AB is a point of local maxima or local minimum, then f prime c is 0. This is a fundamental theorem here. A lot of theorem comes from this. Well, what do you mean by local maximum? Local mean? So which means that if the graph looks like this, So there are points where this point, so here this points, this, this, this. There are a few points here, right? So here, see here, this is not the maximum because this is bigger than this. But if you look at a small interval and restrict that function, so this will be maximum. Similarly, this here, it may not be minimum. So it is less than this. But if you restrict this function here on a small interval, then you'll see that here this gives a, this point is the minimum. This is the minimum. So this is local mean. So local mean in a means, or local max means restricted to a small interval and looking at the minimum or maximum. So a point C in AB is said to be a local max if a point of local max here. Local maximum if there exists a neighborhood IC of C such that if C is bigger than Fx for all x belongs to IC minus C. Similarly, one can define a point D belongs to AB maybe I put D here and C here. No, this is fine, I think. Did I write it here? Fc equal to alpha minimum, so that's fine here. D here and C here. Is said to be a point of local mean if there exists a neighborhood IC of C such that Fc is less than Fx for all x belongs to IC minus C. All right, so these are local mean and local max. And theorem says when there is a local max or local mean for a differentiable function, then the derivative vanishes. So derivative vanishes means the tangent is parallel to x-axis. Well, let us give a proof of it, proof of this theorem. So this is very important theorem. All the mean values theorem, Rolle's theorem will come from here. So how do you prove? So before proving, let me just say a few things about the technique. The technique of the proof is as follows. So it's actually to define a function G from AB to R by this one. Gx is equal to fx minus fc by x minus c when x not equal to c, and f prime c when x equal to c, right? And check this g is a continuous function on AB, right? As x tends to c, this limit goes to f prime c, right? Because f is differentiable. Therefore, g becomes a continuous function. Otherwise, this is already continuous, and 1 over x minus c is continuous, so this g is continuous on whole of AB. All right? So is this clear that g is continuous?
Yes, sir.
So the main idea of the proof is this. Okay, let's go into the proof now. Assume C belongs to AB is a point of local max. All right, local maximum or local maxima, whatever you say, no problem. So call this one. We define function g from AB to R as in 1. Right? So assume that f prime c is not equal to 0. We want to arrive into a contradiction. Right? We have to show f prime c equal to 0. So assume f prime c is not equal to 0. So, and what is f prime c? Which is gc, right? X equal to c, it is the value of g is f prime c. Right? So assume this is non-zero, so either f prime c will be greater than 0 or f prime c will be less than 0. So we divide into two cases. So case 1, f prime c is greater than 0. This means g of c is greater than 0. Since g is continuous on AB, there exists epsilon greater than 0 such that gx is bigger than 0 on c minus epsilon to c plus epsilon. All right? So is this clear? Continuity gives you, so a continuous function, suppose it is greater than 0 at one point, then it will be greater than 0 in a neighborhood. Is this clear?
Yes, sir.
Yeah, this is also last semester's thing. All right, now let us see what it means. So it means fx minus fc by x minus c is greater than 0 on c minus epsilon to c plus epsilon. C plus epsilon. So this implies fx is greater than fc on where x bigger than c, so that is on c to c plus epsilon. and fx less than fc on c minus epsilon to c. So this implies x equal to c is neither a point of local max or a point of local mean, right? So here it means this c is not a local max, and this means it's not a local mean. All right. So this gives a contradiction in this case. Right, so this is a contradiction, right? Because we assume that x equal to c is a point of local max or local mean. Now case 2, f prime c is less than 0. So this case cannot occur because we reached in a contradiction. So this means gc is less than 0. Again, since g is continuous on AB, there exists epsilon greater than 0 such that gx is bigger than 0 on c minus epsilon to c plus epsilon. All right. Now this implies, oh sorry, it's less than 0, right? This is less than 0. So that means fx minus fc by x minus c is less than 0 on c minus epsilon to c plus epsilon. This implies fx less than fc on c to c plus epsilon and fx greater than fc on c minus epsilon to c. So is this clear? We are repeating things. The main idea is, yes, main idea is this one, defining the function g, nothing else, and then continuity. Yeah. Any question here?
Sir, I couldn't understand why gx is becoming positive if f dash x is also positive, f dash c or gc is positive.
Yeah, because of continuity, right? So what is f dash c? It is g of c at x equal to c, right? So this f prime c is equal to g of c, right? And g is
Yeah, right.
continuous. At one point it is positive means there exists a neighborhood where it is positive. Do you know the proof of it?
Mm, Probably I have done this on the first semester, but I forgot that.
Yeah, so you have, if you don't remember, then you go back and check.
Okay.
Okay, so this is very important stuff in continuity. So whatever subject you go after this, it will be useful. So it will be an investment of your time. So no problem. So you go back and see why this happens. It is just by definition of continuity. Okay. All right. Any other question? Alright, so here that again implies that x equal to c is neither a point of local max or a point of local mean. So this implies, so this is a contradiction. This is a contradiction. Therefore, this implies that f prime of c is equal to 0, right? So it cannot be less than 0. F prime c cannot be greater than 0. Therefore, it has to be equal to 0. All right? This is very simple once you define the right function. All right? Now note all the points. The converse of the theorem is not true. All the points where f prime x equal to 0 may not be the point of local max or local mean. So for example, if x equal to x cube, so here it's something like this. So at the point 0, this point is neither local mean or nor a local max. But they say prime at 0 is 0. Right? So these things are well known to you. And what I put a remark. So how to determine local max local mean. Well, we'll not come into we'll come back here, but let me just make a remark here that for determining the points of local max or a point of determine whether sorry whether a point is a point of local max or a point of local mean we need to look at higher order derivative. One nice condition is as follows. F prime C is equal to 0 and F double prime C is greater than 0 implies C is a point of local mean. And F prime C is 0 and F double prime C is less than 0 implies C is a point of local max. And when F double prime is 0, then you need to go to higher derivatives. And if F double prime C is equal to 0, again F prime C is equal to 0 and double prime C is also 0, then you need to we need to go to higher order derivatives. So I'll come back to this once I finish about the first about the description of first order derivatives. So our first goal is to show what information can be provided by first order derivative about the function. Then we'll go to the second order derivative mostly. And then, of course, the higher order derivative will come only in this case, where the second order derivative is 0 and in the maximum minimum. All right. So we want to determine how the function behaves. And it is mostly determined by first derivative. When the first derivative is 0, those are called singularities. And in this case, sometimes those are points of maximum or local max or local mean. And what happens at those points? Right? That is our question. And for that we'll be looking at the higher order derivatives, mainly second order derivatives, and that will tell you in which direction this function is bending. All right. The graph of the function is bending towards. But this theorem is fundamental. Yeah, this theorem is very important. And we know that F prime C equal to 0 means the tangent line of the graph of f is parallel to x-axis.
So does this condition hold only for local maxima and local minima, or in general, irrespective of whether it's local maxima or local minima?
So the point is, where there is a maximum or minimum, the derivative will be 0.
Yes, sir.
So that is, I mean, whether you consider it as a global max, a global mean, or local max, local mean, doesn't matter. But this actually, I mean, if you want to determine the maximum, you have to look at all the local maximum and then look at the maximum of those.
So C has to be a local maxima, local minima here, right?
Yeah, global maximum is also a local maximum, right?
Yes, sir. Yes, sir.
Yeah, so that point will also be there. So it will be consisting of all those points. All these points where there is a local maximum, local minimum, and something more, right? Like this one. See here, there is no local max, local mean, but still derivative is 0.
Yes, sir. Over there, the tangent won't be parallel to x-axis, right?
Tangent is x-axis only.
So what is the definition of tangent exactly? Like, does it mean? I'm not understanding how there will be a tangent, which is
Yeah, so
y
it is a
equal to 0.
differentiable function, right? So it is a differentiable function.
Yes, sir.
Yeah, so tangent line is this will be the slope of the tangent. F prime 0 will be the slope of the tangent.
Okay, sir. So the
So
tangent is
it is like
defined as.
this. You are going. It is this. From this side, you see it will be tangent. So it is not crossing as such. So it is tangentially going like this.
Oh, okay.
Right. So yeah, it is not crossing. So my drawing is little bit straighter. So it is not straighter. It is going tangentially here.
Yes, sir.
It is coming tangentially this side also.
Yes, sir. Yeah.
So that's why you'll get this as tangent. Tangent will be parallel. That does not mean it will be always local max, local min. So this is called saddle point.
Sir,
Yes.
Sir, also, is it really necessary that the global maxima will occur at a point where the derivative is 0? Where the derivative
Of
value
course.
is 0?
Yes, derivative
So
is 0.
suppose we have an increasing function on a to b such that suppose we have a strictly increasing function on a to b. Here,
So you have to be in open interval in this case, right? See, the theorem is in an open interval. And inside open interval, your maximum attains. Yeah, it can be attained at the end point, but in this case, that might not happen. The derivative might not be 0.
yes, so that's what I was saying. Like, if we have such cases where the maximum is attained at an end point, then derivative may not be 0 as well.
Yeah, at the end point. So function is not behaving. I mean, you cannot say the function has a maximum there. So your restricted function may have maximum there. So you don't know at that point. So suppose it is increasing, like fx equal to x, something like that. Okay. So at the end point, well, you know the behavior of the function. It is increasing function. That's it. So then endpoint will be the maximum. And in this case, of course, this theorem doesn't hold.
Okay, so
and that point is not a point of maximum if you increase a little bit the interval.
okay, sir.
Not even local max.
Yes, sir.
All right. Yeah. Any other question?
Sir, I thought the theorem said that a continuous function has a maximum and a minimum only on a compact set and
Of course, yes. Continuous function has maximum, minimum. No. It might happen that in an open interval also you have maximum, right?
But it's not necessary, right?
Yeah.
We
It's
may
not
not have one.
necessary. So it is. This the converse of this may not be true, or
No,
the this. So
uh,
here in this case, see compact set. If you look at closed interval, it will of course will have maximum and minimum. So there it actually contains endpoints also. But for the endpoints, you don't know this derivative condition. You don't know, right? Here it is a bit. I mean, relaxed. You need an open interval to get the derivative to be zero, right? You have to know the both side around that point.
yes, sir. But what I'm wondering is if now since we've moved on to the open interval a comma b, uh,
Yes.
it is possible that there is no maximum or minimum in this open interval, right?
Yeah, it's possible. Then what happens?
Then the derivative is not zero at any point on a comma b.
Yeah, but then you know the behavior of function.
Right. No, I was just yeah. Okay.
Yeah, then you know the behavior of the function. No, it will then occur at the endpoints.
Huh.
It will then occur at the endpoints and the function will be actually increasing or decreasing.
Huh. Yeah. Right.
So that is a very simpler kind of function.
Hmm.
Yeah, that part also we'll discuss in the next time.
Okay, sir.
Yeah. So when there is no such local max or local mean, then what happens for differentiable function? Well, for increasing and decreasingness, we need a class for that. Yeah, any other question? But this theorem is very important. A lot of theorems will come. So at this point, let us look at the corollaries of this theorem. And after that, we'll look at what happens when there is a no local max, no local mean. And then what happens? Okay, so here what I was drawing is that this means the tangent line parallel to x-axis. Right, so parallel to x-axis. Okay, so next time we'll see the corollaries. Most of the mean values theorem will come from here. So this is the fundamental in this case. All right then. So you have a tutorial today. So all right. Okay. Bye.